Okay, today's lesson is lesson number 51, solving systems of linear equations and inequalities by graphing. These are the steps for solving systems of linear equations. This should be review from Algebra 1, but if you want to take a second and write these down, just so you can remember. You're going to arrange the equations in slope-intercept form, and then you graph using your slope, which is m, and the y-intercept b. Then you look and see if the lines intersect and where they do, and check your answer by plugging in the point to both equations. The three different cases are listed below. We can either have no solutions, which means the lines look like this. They're parallel, so they never cross. One solution means they just cross at some point, and we write our point as an ordered pair. That's the solution to the system because it's where both lines exist. The third option is that we have infinitely many solutions, and that occurs when the lines overlap at every point. So essentially you just have the same line. Here's some examples. Again, you guys should know this from your earlier algebra classes, but we'll do a couple examples just to refresh. So here, this is already in slope-intercept form. So we're going to graph using the b, which is our y-intercept. So plot a point at 0, 4. Then our slope is 2. So we'll rise 2 and run 1 to make our next point here. And this line then looks like this. Okay, our next line has a y-intercept of -1. So we'll plot a point at -1 on the y-axis and use the slope of -1/2, which means I'll go down 1 and then run 2. And my second line then looks like this. And as you can see, the lines intersect at the point -2, 0. So that's my solution to the system. This next example, you need to rearrange these two equations into the correct form first. So we can do that by subtracting 3x, which gives me 2y is equal to -3x plus 6 dividing by 2. I have y equals -3/2 x plus 3. Then the second equation, I just need to add 2x. And I have y equals 2x plus 3. Again, we just graph using the y-intercept and the slope. So this first equation, I have a y-intercept of 3, and the slope is -3/2, so I go down 3/2. And the next equation, I have a y-intercept of 3 again, and a slope of 2, so I go up 2/1. And there's my second line, excuse me. And these intersect as well, so my solution is at the point 0, 3. This next one I would also have to rearrange, and I end up getting y equals x minus 3, which means that the first equation and second equation are exactly the same. So when I graph those with -3 as the y-intercept and a slope of 1, my lines are exactly the same, right? They overlap, so I have infinitely many solutions. All right, and the last example, if I move the terms around in this equation so that I get into slope-intercept form, I have y equals 1/2 x minus 3. So these equations both have the same slope, which means they're going to be parallel. So they'll never intersect, which means I have no solution. Okay, here's a little bit more difficult of a concept. This is solving systems of linear inequalities. Here are the steps. So first we're going to arrange into slope-intercept form again, and we'll graph a line using the slope and y-intercept. But instead of an equal sign, we're going to have these inequality symbols. So when you see those, you're going to look to see if there's an equal involved. So if you just have less than or greater than, you're going to use a dashed line. And if you include the equals, so less than or equal to or greater than or equal to, you're going to use a solid line. Then you'll shade the appropriate region, and the solution of these systems is a region. It's the space where the two shaded regions overlap. And you'll verify by plugging in a test point. So we'll see how this works with the next examples. Here they're already in slope-intercept form, so I can go ahead and graph a line for each of these. Again, this is a greater than and a less than, so they're both going to be dashed lines. For my first inequality, I have a y-intercept at 4 and a slope of -3, so I'll go down 3 and over 1. And again, I'm going to use a dashed line. My second inequality has a y-intercept of 2 and a slope of -1/2, so I'll go down 1 over 2. And it's also a dashed line. Okay, then I'm going to look to shade the appropriate region. So for the first inequality, I can see that it's asking for the y values that are less than this line. So I'm thinking on my graph, remember this was our first inequality and this is our second. On the graph I want the y values that fall below this line, that are less than it. So I'm going to shade this area down here. I can also check by plugging in a test point. So an easy test point to use is the origin, which is 0, 0. And I can check, hey, if I plug in 0 for y and 0 for x, do I get a statement that's true? And this comes out to 0 is less than 4, which, yes, is always true. So I want to make sure that when I'm shading, I include 0, 0 in my shaded region. Okay, the next inequality, I have a greater than sign. So I want to shade above the line, right? So over here, for my second line, I will shade above it. And again, I can check with 0, 0. If I plug in 0 here, I get 0 is greater than 2, which is not true. So I shouldn't include the origin. So that means I don't want to shade down here. That would be wrong. So I need to shade the opposite side up here. Okay, then I look to see where the solutions overlap. So my solution to this system is this shaded region in here, this little pie slice where both shaded regions overlap. Okay, for the next example, I need to get these into the correct form. When you're doing this with inequalities, make sure that you're careful to keep the symbol the correct way. So I have 3y. If I subtract 6, I get 3y is greater than or equal to x minus 6, and then I need to divide by 3. So I have y is greater than or equal to 1/3 x minus 2, dividing both of these terms by the 3. For the second equation, if I subtract 2x, I have -2x minus 1 is less than -y, I want y by itself, so I'm going to divide everything by a -1. Remember that when you have an inequality and you're dividing by a negative, you need to flip the sign. So dividing these by -1, I have 2x plus 1 is greater than y, which if I want to read it this way, it's the same as saying y is less than 2x plus 1. Again, I can graph both of these as if they were lines. This is going to be solid because it has the equal to symbol, or it's the greater than or equal to, and then this second line is going to be dashed because it's just less than. So the first line, I have a y-intercept at -2 and a slope of 1/3, so up 1 and over 3. And that's my solid line. The next one, I have a y-intercept of 1 and a slope of 2, so I'll go up 2 over 1, and that's my dashed line. Okay, now I'm going to shade the appropriate region. So on the solid graph, for the solid line, I am looking for the values that are greater than or equal to that line. So I'm going to shade above. I want the y values that are bigger than the line. For the dashed line, I'm looking for the y values that are below, right, that are less than the line, so I'm going to shade the y values that are less than it. And I can see they overlap in this section in here. Again, I can check with each piece with a test point, or when I'm done and I have this shaded region, I can make sure this is the correct solution by plugging in a test point. Let's say 1, 1. Okay, that's in this double shaded region. I'm going to plug that test point into both of these equations to make sure that I shaded the right area. So if I plug it in here, I get y is greater than or equal to 1/3 minus 2. This is the same as saying 1 is greater than or equal to 1/3 minus 6/3, or 1 is greater than or equal to -5/3. 1 is definitely greater than a negative number, so that's true. Over here, if I plug in 1, 1, I get 1 is less than 2 plus 1, so 1 is less than 3, and that's also definitely true. So I shaded the correct region. Points in here make both of these inequalities true. Okay, and one more example. If I add 1 here to get in the correct form, I have y is less than or equal to -2x plus 1. So this is going to be a solid line because it's less than or equal to. I have a y-intercept at 1. My slope is -2. And solid line. This is also a solid line, and you'll notice there's no m or x term here, so we have a slope of 0. Remember, when I have a slope of 0, that's the same as a horizontal line. So I'm going to have a horizontal line at y equals 3. Fix that. Okay, then I want to do my shading, right? So for the horizontal line, it's asking for y values that are less than or equal to 3. So I'm going to want to shade all of this, right? All of these points have a y coordinate less than 3. For the second line, I guess it's actually the first, but for this line, I want the y values that are less than or equal to the line, so I'm going to be shading below, which is this area all in here. So I can see that the overlapping part is this big section here, and again, I could check that with any test point in there. And here's another example that you guys can do by first solving each of these putting them into the correct form, then graphing the lines and shading the appropriate region. I'm going to stop here though, so that's it for today's lesson. Thank you.